The new section 1.3, so which is a rather long section, so spread out over 2 classes. So same thing as before. I have 8 pages of notes. So when I get through 4 of them, or maybe slightly more than that, we're done. Finish the rest on Monday. Okay. So this section we get more theoretical. Convergence theorems for Fourier series. All right. Now you think that when a theorem is actually named, especially when it's named after somebody, you think, oh, it's supposed to be a really big theorem that's so difficult to prove. Well, at least for weakening assumptions a bit, this one's rather easy to prove. It's the Riemann-Lebesgue lemma. Funny thing is, whenever I'm typing or writing out Lebesgue, I just, in my head, I go, Lebesgue.
Well, I think everybody does that.
yeah, just to make sure that I spell it right. But yeah. So the Riemann-Lebesgue lemma.
It's so nice. This is a review from functions of a real variable.
Oh, really? Okay.
Yeah, we're doing Lebesgue measures right now.
Oh, okay. Yeah. So this is where I feel fortunate that with my name, the phonetic pronunciation is the correct one. So, okay. So if F is piecewise continuous. So this is my abbreviation out of sheer laziness for piecewise. So if F is piecewise continuous on interval AB, then what we have is we take the integral of F on AB times cosine kx or sine kx, so it doesn't matter which one. And then we take the limit of that as k goes to infinity, then we get 0. So intuitively, this makes sense just because as k increases, you have more and more oscillation, and you end up having positive area cancels out by negative area, like thin slices of positive negative area canceling each other out. Now, I'm not going to prove this theorem as written. So with these assumptions, that proof probably would be rather complex. And I already have a long proof queued up for today, so I don't have room for 2. So we're going to do an easy proof in the case of weaker assumptions. Now, the book doesn't use notation, but it's good notation to know. Yeah, you may have seen it in another class. So if F is in C1 of AB, so you know what that means? When we say F is in C1 of an interval?
Is it complex? Has something to do with complex numbers?
No, not complex numbers. Well, first just the C, because also it's a thing to say F is in C of AB. So the capital C, in this case, what does that refer to? What? Well, the AB is a domain. So when we say F is in C of a domain, what does the C mean in this case? What C word are we abbreviating? Continuous. Yeah, so if I just said C of AB is a space of continuous functions on AB. But now I have C1. So when I throw out 1 in there, what does that mean? Yeah, if a dwarf is differentiable, continuously differentiable. So this means that this set of all functions that have at least one continuous derivative on AB. So in general, like Cm of AB is functions that have at least m continuous derivatives. Okay, so I'm going to limit myself to that case. So the proof is actually one equation long. So because what we can do is integration by parts. Oops.
Oh, we're doing integration by parts here? Amazing.
I forgot my dx. Okay, so when we do integration by parts on this, so that f be the u, and then cosine kx is the dv. So I have f of b sine kb minus f of a sine ka all over k, assuming k is not zero. And then the other term is, make sure I'm getting all this. Okay. Integral of 1 over k f prime. So this is why I need the assumption of continuously differentiable. Now, if I think differentiable might be good enough, but if I assume it's also first derivative is also continuous, then the integral is guaranteed to exist and be finite. So that's what I needed here. Okay. So that's the integral we get, and what we can see is with f being f and f prime both being continuous, both this integral and this is and in this part, they're guaranteed to not blow up to infinity or anything like that. And so this part, the numerator, guaranteed to be bounded because AB is a closed interval, also known as a very simple instance of a compact set. So very important fact that tends to be taught in real analysis classes is that a continuous function on a compact set is guaranteed to have a maximum and a minimum. So in other words, this is bounded. This integrand here also bounded. So we can bound everything. Now, we'd like k to go to infinity. So everything here is independent of k, or only slightly dependent on k, like sine is between -1 and 1. So this numerator and this part of the integrand I'm highlighting here can be bounded independently of k. Then we'd let k go to infinity, and everything goes to 0. So, okay. All right, so that was a bit of an lengthy explanation for just one equation, but still. There's a lot of little tidbits like that that really help save you in proofs to take advantage of, and help make your proofs more rigorous, like knowing when something can easily be bounded, and so on. Okay, so now I think about it, in the case where f is when it's only known to be piecewise continuous, I haven't seen the proof for that case, but chances are what would happen is you would then focus on each subinterval of AB, where it's continuous. So then, now you don't have continuously differentiable, but so you just have to still use a different approach to show that all this goes to 0. So this is something that's really going to help us because these expressions, f of x, integral of f of x cosine kx or sine kx, that's where we get our Fourier coefficients. So under mild assumptions on f, we can be certain that the Fourier coefficients of a function of f of x are going to go to 0 as k goes to infinity. And we saw that in all the examples last time, and we also saw that the smoother a function is, the more rapidly they go to 0. And you can kind of see why here, because suppose f had more derivatives than this. I could do integration by parts again. And I get higher powers of k in the denominator. Now, in the case where f is a 2 pi periodic function, then these boundary terms will go away, because everything in this numerator would be 2 pi periodic. So that's one. That's actually how a book written by my co-advisor, I remember seeing, or co-written by my first advisor, was how that is proved. How the decay rate relates to the smoothness of a function. Alrighty. So I'm showing you this because this is a result that's going to help us with the main proof of the day. That actually goes on for 3 pages and requires 2 lemmas. So strap in, it's going to be a bumpy ride. Okay.
But it'd be a fun ride.
Well, I had fun writing it up, so.
And you didn't even cite from Borbati.
Oh. Yeah. Well, okay. So actually,
I'm taking a guess there. I haven't seen your notes yet.
Oh, it's still based on what's in the book, but theorem 20. Okay, so 1, 2, 3, 4, 5. Okay, so actually, the proof in the textbook goes on for 5 pages, so I condensed
Oh, hey, a more efficient proof.
Yep. And the dilemmas here I find one in particular quite interesting. Something that I've seen used in other contexts throughout numerical analysis. So, okay. Whoops. All right. So. So suppose our function little f of x has the usual Fourier series, big F, okay, and as usual work with the interval minus pi to pi. So setting our usual notation. AK cosine kx plus bk sine kx. And so we say that f converges, so big F converges to little f at a given point x if the limits, as big N goes to infinity, of the truncated Fourier series. So we only keep the first n terms. Ends up being equal to the value of little f of x. So really we're talking about point-wise convergence. Sometime later we will see uniform convergence. Okay. Now, okay. So this will allow me to state the main theorem here. All right. So if f is continuous and 2 pi periodic. And if the derivative exists at a particular x, that's really all we need for this result. Then we can say that big f of x actually converges to little f of x. So a Fourier series does converge at that point. All right. So what we're going to do is just go ahead and start with the truncated Fourier series that we see here, but I need to get it into a different form. Okay, so let's begin the long proof. So I'll define Sn of x to be this truncated Fourier series. Cosine kx plus bk sine kx. All right. So what I'm going to do is, I have formulas for all these Fourier coefficients, so I'm going to dump them in here. So for a0, it's 1 over 2 pi minus pi to pi f of t. And then similar for the AK and BK. All right. Now, all right, so for AK, I have 1 over pi ft cosine kt dt. Should run out of room here. Okay, and then similar for sine. Okay. All right. Oh my God. Forgot some things. Cosine kx here. Sine kx there. Okay. So AK cosine kx plus BK sine kx. All right, and then what I'm going to do is, okay. So I have in each term here, I have integral of f of t dt, and I have at least a 1 over pi. So that's something I can kind of factor out. So and then the sum, and the cosine kx and the sine kx, I'm going to move all that inside the integral. So by doing a lot of rearranging, I can have out front 1 over pi integral of f of t times a whole bunch of other stuff. So I'll have 1/2 from here, and then I'll have the sum. And then I'll have, from here, the cosine kt times the cosine kx plus sine kt sine kx. dt. Well, actually, the dt should be outside the parentheses. Okay. Now, that expression inside the sum, cosine kt cosine kx plus sine kt sine kx, well, I can condense that using a trig identity. For this is just cosine k t minus x. So now the truncated Fourier series has a rather simple form. So we have this integral of f of t times this 1/2 plus sum of all these cosines dt. All right. but it's still a summation. It turns out that we can condense this even further. So we can write this summation as a expression in closed form. And by closed form, I mean that there's no summation anymore. There's not a number of terms that's dependent on n. There's just a single expression. So we like closed form expressions, certainly, for practical computation, but also for theoretical purposes. So any questions about up to this point? One page down, free to go. Okay.
It's going too fast. I'll miss it when it's gone.
So I'm going to focus on just this piece, the piece in the parentheses, and see what we can do with that. Okay. Now, so I'm going to use this formula that everyone should know, because it's useful so often. Okay. The partial sum of a geometric progression. So that'll be r to the n plus 1 minus 1 over r minus 1. Okay. So, to take an abstract version of that expression in parentheses down below, I'm going to have 1/2 plus the sum of this cosine ku. So u up here refers to the t minus x down below. So I'm going to come up with a simpler form of this expression just in the general case, and we're going to use that down there. Okay. So this is where things begin to get ugly, believe it or not. Now, first, I'm going to rewrite this. I'm going to write to 1/2 as minus 1/2 plus 1, but I'm going to take the 1 and put it into the sum. So I can actually have a sum from 0 to n of cosine ku, because when k equals 0, cosine ku would just be 1. And the reason I'm doing that is I want to get to this point where I have the sum of powers of something from to the 0 power all the way up to the nth power. But cosine of ku is not exponent. It's not an exponential expression, not by itself. But cosine ku is the real part of e to the iku, or I can write it this way, e to the iu raised to the k power. Because e to the iu is cosine u plus I sine u. If I raise all that to the k power, that's cosine ku plus I sine ku. Because you multiply the argument to the complex numbers. So now I have a geometric progression, or the partial sum of a geometric series. And now I can use this. So I get, oh, whoops. Sorry for those who are watching. Okay. All right, well, then it occurred to me, like, well, of course, now we can pause that and get all that down before I continue, before resuming me so I can continue. Okay. So I'll try to be better about that in the future. Fortunately, all this isn't enough. Okay, so 1/2 plus real part. So now this sum can be replaced by this expression right here, where r is equal to e to the e to the iu. So I'm going to get e to the I n plus 1 u minus 1 over e to the I u minus 1. All right. Okay, so now the sum is gone. This is an expression in closed form, but I need to get it into a simpler form than this for what I'm going to do later. Also, I don't really want to have complex numbers. I know that this expression I started with is real, so I want to get back to something that can easily be seen to be real. Okay, I'm going to leave the last line down there so I can refer to it later. That requires careful erasing.
I missed the opportunity to say don't slip.
And for bad and painful. They probably would have invited a slip. All right. So, what I'd like to do is take advantage of the fact that cosine theta can be written as minus, actually, I don't want cosine, sine. E to the I theta minus e to the minus I theta over 2I. So when I have a difference of complex, where the arguments are negatives of one another, then I can write something as a sine. I don't have that here, but if I do a little factoring out, then I can do that. So, okay, it looks like I have, wait. No, I don't know. So, okay, so minus 1/2 plus the old part. So I'm going to factor out of the numerator plus 1 u over 2. And the reason I'm doing that is now what will be left in the numerator is e to the I n plus 1 u over 2. So I've just broken the exponent in half, pulled half out and left the other half in. But then that means over here, I'm going to have, where I had the 1 before, it's going to be e to the minus I n plus 1 u over 2. So now I have that situation where I can use sine. I have a difference of complex exponentials with arguments, exponents are negative to each other. If it was a sum of such exponentials, that would be cosine. And I do the same thing down below. Down below, I factor out e to the I u over 2. Then I'll have e to the I u over 2 minus e to the minus I u over 2. So now, the top can be written as 2I sine of something, and the bottom can also be written as 2I sine of something. The two i's will cancel out, making this fraction real. Actually, here too, I can simplify. It's not real yet, but I can simplify it, and I get I can subtract the exponents. So I have e to the I n u over 2. Okay, and then this fraction becomes sine n plus 1 u over 2 over sine u over 2. Okay. Now I need to take the real part of all this. This already is real, so I can focus on this. Well, the real part of a complex exponential is the cosine. So what I get now is minus 1/2 plus cosine nu over 2, and then I have this, the rest of it the same. N plus 1 u over 2 over sine u over 2. Okay. Now, I have a cosine times this sine up top. When you have a product of a cosine and sine, you can use a product to sum identity to rewrite it into a nicer form. So that will give me minus 1/2 plus, that denominator is going to stick around, but the product of some identity is going to introduce a factor of 1/2, so I'll throw a 2 in down there, and that cosine times that sine will give me 1/2 times these terms. Okay, so sine of, what I do is I have sine of this plus this, and also their difference. Okay, so n plus 1 u over 2 plus nu over 2 plus sine n plus 1 u over 2 minus nu over 2. Okay. Now, if I look at this difference here, n plus 1 u over 2 minus nu over 2, that's just going to give me sine of u over 2. Which cancels with the sine of u over 2 down here, so that this second term is just 1/2. But cancels with the minus 1/2 out here. So, gone. Gone. So, what's left? Okay. I don't like a glare over there, but okay. So, ultimately, I'll bring this down here. So, 1/2 plus the sum from 1 to n of cosine ku. Okay. Maybe if I stand right here, I can shut out enough of the glare. Is equal to what's left, and that is sine n plus 1. Well, it's a sum of these together, and I didn't bother doing the algebra because you guys teach 101. Okay, n plus 1/2 times u. So if you add these together and simplify, you end up with sine n plus 1/2 times u, all over this 2 sine u over 2. Okay, so this is one of the lemmas in the notes that condenses this sum of cosines into this relatively nice closed form expression. Still kind of ugly, but there's no summation. So now what I can do is take this expression and use it to condense that whole part in parentheses. Okay. Into something a whole lot smaller that would be easier to work with, certainly because, if for nothing else, because there's no summation anymore. Okay, so any questions about what happened here before I erase everything to go to the next step?
No, I will just observe that it is nice to recognize that we can go from summations to having to use Abel's lemma.
Oh, okay.
And do the real joy of going between summation by parts and integration by parts, which of course I can get real fun.
Yeah. Because you triggered these can now. Yeah, it's weird that I went through a period of years where I forgot them. But once I start doing this kind of thing, there's no way I'll ever forget. Okay, so alright, so about to finish the second page. Okay, so I'm pretty much on track. Time-wise. Because now the board is a terrible mess. So once I make that substitution back into the Fourier series, so the truncated Fourier series at x is 1 over 2 integral minus pi to pi. So I have f of t, and the expression that I just derived, so that'll be sine n plus a half, and u is t minus x. So putting that back, all over sine t minus x over 2. Okay. Now, for what I'm going to do next, introduce some notation. So this whole thing in parentheses, I'm going to call Pn of okay. So, because now I need to prove another result. About more abstract version of this, of n plus a half u over sine u over 2. Okay. Oh, whoops, I'm supposed to incorporate the 1 over 2 pi into that. Okay, so really, so that's in there too. So to rewrite this more properly, let's be too lazy to transcribe my notes. It's integral minus pi to pi f of t Pn of t minus x. Okay. So I'm looking at this on my screen here. It's hard to tell that this is even an f. Is that better? Yeah, it's better. Okay. So now I need to prove something about this Pn of x. So 1 over 2 pi is lumped into it. I'm going to take the integral of just that. So integral minus pi to pi of p n of u du. Now I'm actually going to kind of undo the result I had before because it makes the integration easier. So first I can integrate, right, this. So it turns out Pn is an even function because sine is an odd function, but an odd divided by an odd is the even function. So this is the integral, 2 times the integral from 0 to pi of Pn of u. And so now what I can do is use the result from before, because if I, so this is 2 over pi, so I'm going to take the pi out, and what's left is 1/2 times all this, but that's the exact expression I derived before. That's equal to that summation I had that I was so anxious to get rid of, but now I need it again. So 1/2 plus cosine u all the way up to cosine nu du. Okay. Because even though I want this as sine for various reasons, for computing integral, this is easier. So what do you get? Because this is an easy integral to work out. We get u over 2 plus sine u plus sine 2u over 2 all the way to sine nu over n with limits 0 and pi. So why does this work out really nicely for us when we plug in the limits? Yeah, almost everything is 0. All those signs, you plug in pi and 0, you get 0. So everything's gone. Well, and in the last term, this is the only term that sticks around. The 2's cancel. So what are you left with? But you also plug in limits there too. 1.
Yeah.
Big old 1. So what's so amusing is this, perhaps in undergrad classes mainly, where I give a really nasty thing to work out, like nastier than this, and they get all the way to the end after the reams of paper, and the answer is something like 1. Like, 1? All that work for 1? Yeah, it's like, that's how you know you got it. Because in undergrad classes, especially, the numbers are supposed to work out nicely. Okay, so now we're almost to the end. Okay. So because the integral is 1, x, I can rewrite that as integral from minus pi to pi, Pn of t minus x dx. Now, so really what's happening is t is between, one thing I kind of glossed over here, t runs between, oh wait a minute, I goofed up here. That should be a t. From the point of view of the integral, x is a constant. Okay. So t is running between minus pi and pi. And I replace t minus x with u, which would lead to a different interval of with 2 pi, but it ends up not mattering because Pn of u, you can easily see from a definition, is a 2 pi periodic function. So it doesn't matter which interval of width 2 pi I'm going to integrate over, I'm going to get 1. So what I've done here is I've done a very elaborate way of multiplying f of x by 1. And the reason for that is now I can say that the difference between f of x, what I hope to be the converged Fourier series, and the partial Fourier series, I can write as this integral of f of x minus f of t, Pn of t minus x dt. Okay. So this whole thing, I want to show that it goes to 0 as n goes to infinity. Because now, if I show that, I've shown that this Fourier series converges in the limit as the number of terms goes to infinity. So this is my error. So now I want to see what happens that error as n goes to infinity. Okay. Now, so what I'm going to do is I'm going to bring into it the definition of Pn. So I'm going to substitute that into the integral. Okay. So, all right. So f of x minus Pn of x.
I couldn't see the word on the where it approaches 0.
Oh, my computer's in the way. All right.
No. I can't see. Is it W-A-N-T, right?
Yeah, want.
Okay.
Yeah, I want this to go to 0. That reminds me when I was at Stanford, so I was in class, and so Professor Wright written some equation on the board about something z equals 0. And so a student asked him, why did you set that equal to 0? And he said, because I want to get rid of it. So that's kind of what I'm doing here. Math is such a violent subject. No. Okay, so now taking this definition of Pn will give you 1 over 2 pi integral minus pi to pi of, okay, so I have f of x minus f of t, and then I have a denominator for Pn, so that would be sine x over 2, okay, and then I have the other sign from the numerator, over here, sine n plus 1/2 t minus x dt. All right. Now, all right. 0. I'm going to focus on this part right here. I'm going to call g of t. Because we're thinking of x as some fixed value, and t it's varying from minus pi to pi. This function is now we're already assuming that f is actually continuously and the derivative exists at x. But this whole fraction, except possibly where?
T plus x.
So when t equals x, we may have a problem. Now, it occurred to me that minus pi to pi, x can be whatever, but forgot to close some parentheses. Okay. Always something, isn't there? So one thing that the book kind of glossed over, I'll have to check on that, is because we have that sine of that angle over 2. If you hit any multiple of pi, then you have a problem. So x. But what if the t and x differ by, well, wait a minute. No, it's not a problem. Yeah, because every multiple of pi, so you can't have t minus x be equal to over 2 be a multiple of pi. So t minus x of 2 pi. But the only time it can happen is once, when t equals x. Because t only equal of with 2 pi. All right, never mind. Just making sure that we didn't miss anything. If it was like sine 2 times t minus x, then we'd have a problem. Okay, so this is continuous, except that t equals x. Or I should say, except possibly t equals x. Let's see if we can make it continuous at t of x equals x, because if we can at least show that the limit of this function at t equals x exists, then we can define a function value for it and make it continuous. As long as, because if there's a well-defined limit, it's a limit that exists from both sides. Okay. So it's converting to the same value either way. Okay. So what I'll do is, so the limit as t approaches x, so some algebraic hocus pocus here. Of x minus f of t, and I'm going to divide by x and then multiply by x minus t, and I still have sine x over 2. Now, I'm going to make x minus t into x minus t over 2 as long as I multiply by 2 over here. See how I delivered that 2 in there. Okay. Now, what happens to this as t approaches x? Well, what happens to that? What does that converge to?
Infinity.
No.
What's this one?
F dash. F dash.
What?
F dash. F
Oh, f prime. Say f dot.
He's a
Dash.
dash.
Okay. That's what you call it? Okay. Well, because different classroom conventions and so forth. Yeah. I don't know. That's a new one. Also, it's not because I'm going to call it f dash in every class I ever teach, just to confuse people. Okay, so that's f prime. What about this? What happens to this as t goes? That limit sine x over x goes to 1 as x goes to 0. So this goes to 1. So and we have 2 variables. So this converges to 2f prime of x. And by assumption, exists at x. That means that because there's a well-defined limit, we can make g continuous by defining it to be 2f prime of x when t is equal to x. So now what we have is some continuous function times this sine. But now we let n go to infinity. So this integral, like what's left over in our truncated series, as n goes to infinity. But how do we know that that goes to 0 as n goes to infinity? What the result lets us conclude that? That was presented earlier today. Lebesgue, the Riemann-Lebesgue lemma. Because that dealt with an integral, minus pi to pi, fx cosine kx or sine kx, either way. So the point is the angle here is going to infinity, or it's going to be a. Well, really, if you use the formula for a sine of differences, you have two terms. One, it has a sine n plus a half t, and the other is a t. Both those terms are 0. And that's it. The result is proved that so if f is continuous and the derivative exists at a particular point, then we are guaranteed that the Fourier series converges at that particular point.
This sign, the denominator is over there. Where is 1? It's supposed to be x minus t or t minus t.
Oh, whoops.
So we need a minus sign outside.
T minus x, T minus x, Okay, this is strange. Okay. Yeah, because they have plus. Although they did a lot of algebraic hocus pocus just to get it to this point. G f of. So I have to wade through all of our notation. All right. Plus x. Okay. Oh. Wait. U plus x is t. Okay, so u is t minus x. Oh, I see what they did. I think. Okay, so the book's definition of g of t is the opposite of mine. They have t minus x. So in that case, all right. Well, here's how I'm going to fix this more easily. Using. I remember one of my own professors doing this when he found that he had made a mistake. Minus right there.
Hey, it works.
But now, well, okay. But that still goes to minus 1. Okay. So that's still minus 2, and then. Oh, okay.
You have to negate the 2.
Okay.
That is possible.
Yeah. So okay. What I really want is since they were with t minus x. Okay. So then okay. Here's what I'll do. I'll say this is x minus t. This is still minus. So because sine is an odd function. So if I swap the x and the t in there, that negates the whole thing. So, okay. So, well, not okay. Now I gotta put no one up. Okay. All right. So, yeah. So what the book does is they have the error swapped. Pn minus f, and that has a positive 2, so my error would have a negative 2 f prime. Okay, so wait, plus 1. Okay, so that, well, now I gotta see what this means for my notes. Okay, actually, I think what I'll do in that case is I'll figure something. Okay.
The problem is that here limit t goes to x, it should be negative gt.
Well, negative limits limit of a negative.
Oh,
So yeah. So because what I'm doing here, since here I have t minus x, but here I have x minus t. So yeah. Okay. All right. All right. So what's on the board is fine. Now, finally. Hang it. But yeah, I gotta fix up something in my notes. Okay, so all right, so well, yeah, throughout the notes I have like t minus x everywhere. So really, I should swap x and t there and there. That's the easiest fix to make. And maybe I'll swap these two also. Then it's more consistent with what's in the book. Yeah, if I had Pn of x minus f of x to give me f of t minus f of x, that would have made a whole lot more simpler. But I'm so accustomed to exact minus approximate. So, whatever. Okay. Now, let's see, what else have I got here? Okay, so all of that was about what happens at a point of continuity. So when f is continuous at a point, but then what happens if it is discontinuous at a particular point, but there's at least good behavior on either side of the this continuity. Okay. Okay, so sorry to everyone who's watching for confusion that ensued, but I assure you what's on the board is correct now, at last. Okay, so just have to make sure all these are consistent. Okay, so. So, first notation and definitions. So if I can say f of x plus 0 is a shorthand for the right-hand limit. We're approaching from the right. Okay, so we're getting closer and closer to x, but from above, from greater values, and similarly f of x minus 0. We look at f of x minus h, but for positive h, that's going to 0. We say a function is right differentiable if f prime at x plus 0, which I define as this limit, f of x plus h minus f of x plus 0 over h. So we're using whatever values exist to the right of x to compute the derivative. So we're not hopping over discontinuity. So if that limit exists, we say it's right differentiable. And similarly, f is left differentiable. So we have f prime of x minus 0 is a well-defined limit. Okay, so we have f of x minus 0 minus f of x minus h over h. Okay. All right, so if that limit exists. So visually, it's kind of like this. You have a function that's well behaved on either side of discontinuity. So this function is not continuous, and therefore it's definitely not differentiable. But if you only focus on values of f on this side, you can form a nice, well-defined tangent line for what f is doing over here. And similarly over here, there'll be different tangent lines, but you can define. So,
Like that. So shouldn't it be minus sign?
okay, let me make sure about that. Okay, which thing? Because right, but where in here?
Ask H how
Limit.
much is then ask H for the left differential.
Okay, wait.
Is it now we asking is it possibly with minus over there or it's supposed to be just plus over there?
Oh, this is supposed to be a plus because that way we are to the left of x. Now, I could say h goes to 0 minus and have a plus h. Yeah. So, okay. Yeah, when I was preparing these notes, like, wait a minute, like, oh, yeah. Okay. Now, I have 10 minutes to make use of these definitions. Okay, so a theorem that about this. No, shut up. Okay. All right. So if f is periodic, piecewise continuous, and left and right differentiable, at x. In the Fourier series, big F converges to the average. This is something I mentioned last time. So the average of the left and right limits. Now, the way you would prove this is very similar to that big long proof I just did, but I'm not going to go through that. So once is enough. I know. Okay. All right. So, as an example, suppose we have fx equals x of minus pi to pi, but then we have the 2 pi periodic extension. This is one of the examples I presented last time. So it behaves like this. Okay. Okay. So the Fourier series of this function is just a sine series because it's odd. So you get 2 minus 1 to the k plus 1 over k sine kx. Now, so if we plug in x equal pi, it's easy to see we're going to get 0 because sine of k pi for any integer k is 0. Now, if you look at what's happening here at pi, from the left it's approaching pi, and from the right it's approaching minus pi. So a Fourier series converges to the average of pi and minus pi, which is 0. So it's an illustration of this theoretical result. That when you have a discontinuity in your function in its 2 pi periodic extension, at such a point discontinuity, Fourier series will converge to the average of the values to the left and right of the jump. Okay. To illustrate these other definitions I gave, for this function, what we have is f of pi plus 0 is minus pi. F of pi minus 0, so left-hand limit is pi, right-hand limit is minus pi. And we can also say that f prime of pi plus 0 is 1, and f prime of 0. So if derivative exists, it's equal to 1, because it's y equals x. So for the, but at multiple pi plus or minus multiple f is discontinuous, of course the derivative won't be defined, but you can define the left and right derivatives, such points, and it doesn't have to be the same, but that would not be true generally. But what we have here is that this is clearly piecewise continuous from a graph, and the left and right derivatives exist at pi, so this is a behavior that we get in Fourier series at pi, but it converges to the average. Okay. So, well, I got to the end of page 4. So on Monday I'll cover the remaining 4 pages after I fix all these mistakes. Alrighty.
It's surprising how easy it is for mistakes to